Well, good evening, good evening, good evening, and welcome back as we're moving along quite briskly here the last few days. We're ready to graduate from a Taylor polynomial up to the big leagues and talk about a Taylor series. But before we do so, I just wanted to review a couple of the key elements of a Taylor polynomial and just really paint a good image here. I found this nice image floating around somewhere on the internet, and we were trying to approximate the sine curve here. That's the black curve you see running through the middle. And this red line that you see is the tangent line at x equals 0, and so that's what we're going to call our first degree Taylor polynomial. And then which color do you think is the second degree Taylor polynomial? Hopefully you went with the yellow curve. And actually that wouldn't be the second degree. What it is it's actually the third degree Taylor polynomial, because the second degree had a 0 for a coefficient and just deleted that term. And then we're going to skip the fourth degree and we're going to go all the way to the fifth degree, and that's going to be your orange one. Your orange function is going to be your fifth degree, and so forth and so forth. Looks like the green is the seventh, and maybe the blue is the ninth, and so forth and so forth. But you can definitely see as the degree of the polynomial increases, then the accuracy of our approximation also increases. And so there's a direct relationship between the degree of the polynomial and the accuracy of our results. Okay, so let's build this up and talk about a Taylor series. What you see on the screen right now is not a Taylor series, but a Taylor polynomial right now. But we're going to try to build it up and make it a series. Now, as far as what you see right now, and this confused us just a little bit the other day, was we're staring at 4 terms right now. Okay, there's the third and there's the fourth term, but it's considered a third degree polynomial. And when we talk about degree, degree is referring to the exponent. So although there are 4 terms, this one would be considered a third degree polynomial, obviously with a finite number of terms. So we just, as far as degree goes, look at the exponent, and that'll tell you what degree your polynomial is. And they're going to mix this up. Sometimes on the AP exam, they'll tell you how many terms they want, and then other times they'll tell you what degree they want, and we just really need to be on our toes. But today, when we talk about Taylor series, all of that's going to go out the window, because instead of having a finite number of terms, we're going to go all the way to infinity. And here's what, after that third term, we're going to go dot, dot, dot. We're going to get up to the nth term. So we got the nth derivative evaluated as c, all over n factorial. Okay, x minus c to the nth power. And I ran out of room, but I need to put a plus sign after that term. Okay, and then another dot, dot, dot. And the key is that dot, dot, dot at the end, this dot, dot, dot at the end is married together with the equal sign. Okay, and basically the dot, dot, dot implies that there is now an infinite number of terms, and our Taylor series is going to be a perfect match with our original function within the interval of convergence. And then of course we swoop in here and we start talking about MacLaurin, and MacLaurin is just a specific version of the Taylor series. It just implies now that we're centered at 0, so we replaced all the c's with zeros. And again, we're just going to finish this one off. We're going to turn it into a series. We've got the nth derivative evaluated as 0, divided by n factorial, x to the nth power, plus dot, dot, dot. Again, infinite number of terms, and it becomes an exact match as long as we're within our interval of convergence. Well, you'll notice our title today at the beginning of the lesson, it was called the Taylor series and the Big Four. And there are basically 4 types of functions that the AP thinks are so important that they're going to expect us to memorize the MacLaurin series for those big 4 functions. Actually, 3 of them are MacLaurin, and 1 could be, maybe not. But anyway, what we did in class the other day was we built a 5th degree Taylor polynomial for the sine curve. And so what I did is I just recalled what we did in class the other day for part of our assignment. And we got this far, and it was really cool because we saw that a lot of these terms ended up, the first, the original term canceled out because of the 0, and the second degree term canceled out, and the 4th degree term canceled out. In other words, all of the even degreed terms canceled out. And what you ended up writing the other day, I think we had p sub 5 of x for the 5th degree polynomial. And your notation right there is very important. That's something we put a lot of emphasis on. And then we've got 1 times x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th, and we stopped there the other day. Now, if we had to go further, could you project the next term? I think you'd all say that the 6th degree term is going to drop out, and then we're going to end up with minus, whoops, I forgot my factorial there, minus 1 over 7 factorial x to the 7th, okay? And what we're going to try to do now is morph this into a Taylor series today. Let's see what we got here. The first thing I'm going to do is I'm going to replace that notation with actually using f of x. And we've got x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. Now, if you wanted to keep going, we could say x to the 9th over 9 factorial. But either way, I think you're starting to see the pattern. Our biggest challenge today by a mile is to try to create the nth term. Okay, we need to try to create that nth term and see what happens right in here in the middle. So what I like to do, one of the strategies I've used in the past and it's worked well for me, is I just remind myself that this is the n equals 0 term, that's the n equals 1 term, that's the n equals 2 term, and so forth and so forth. See, basically what we're saying is we had to plug a 4 into the nth term in order to produce this term right here. And then the first thing you'll notice is because it's an alternating series, I'm going to instantly put a negative 1 to the nth power in there. Okay? Then it looks like, if I look at this term right here, it looks like I'm taking my n value, I'm doubling it, and then I'm adding 1. So if I take the 4, I double it, add 1, I get 9. If I back up here, I could take my 3, double it, add 1, I'll get the 7, and so forth and so forth. And then the denominator is very similar. Once you get that exponent, you should get the denominator as well. It's going to be the quantity 2n plus 1 factorial. Historically, we have seen some students forget those parentheses, and that does cost them in the end. So what we've built right here is the infinite Taylor series for the sine curve. And if we wanted to shorten that up just a little bit and put it in summation notation, here's what it would look like. We would say the summation starting at n equals 1 to infinity. Whoops, back that up. That's got to start at 0, my bad. And we'll say negative 1 to the nth power, x to the 2n plus 1 power, all over the quantity 2n plus 1 factorial. And that, ladies and gentlemen, is an exact match with the sine curve. And that's how your calculator is programmed to think about the sine curve. Every time you hit that sine button, the calculator is referring to this polynomial right here that was programmed into it. Whoops, I almost forgot to emphasize this. If you go back up there and look at this polynomial, look at your exponents are 1, 3, 5, 7, 9, etc. So all of the exponents are odd. Back in your old pre-calc days, we used to stress that the sine curve had odd symmetry, and it all ties together here. And I want you to really emphasize to yourself, and this will help you separate sine and cosine in your mind, that sine has only odd degreed terms, only odd. Sine is odd, sine is odd. Okay, the next one we got cooking, we'll call this number 2 in our series Big 4. We've already got sine under our belt, so let's do cosine. And I ran through the first 4 derivatives really quickly. You'll notice that the first derivative drops out, the third derivative drops out, and all we're really left with are the even terms. So contrary to the sine function being all the odd degree terms, cosine is going to be all the even degree terms. And that goes back again to pre-calc where we said the graph of cosine has even symmetry in the sense that it's symmetric with respect to the y-axis. Now as we start to build this series, I'm going to jump right to the infinite series where I'm going to say f of x is equal to 1 minus 1 over 2 factorial x squared plus, we've got 1 over 4 factorial x to the 4th. You could project the next term is going to be minus 1 over 6 factorial x to the 6th. You could then project the next term to be 1 over 8 factorial x to the 8th. You see a very clean, predictable pattern. Of course, the big challenge becomes what's the nth term? And that's where the fun is, I think. And I'm just going to put some little n's here to remind myself. That's the n equals 0 term. This is what you get when you plug 1 in. This is what you get when you plug 2 in. This is what you get when you plug 3 in. And finally, this is what you get when you plug a 4 in. Again, it's an alternating series, so I'm going to instantly put my negative 1 to the nth power in there. it looks like for each of those terms, all I have to do is double my n value. So I've got x to the 2n power all over the quantity 2n factorial. And again, I can't emphasize enough that those parentheses are a very, very, very big deal. If your denominator said 2n factorial and it looked like that without the parentheses, that would be extremely wrong. Let's go ahead, let's rewrite this in summation or sigma notation. Our sigma notation, I'm going to try not to screw it up this time, has to start at n equals 0. It's going to progress all the way to infinity. We've got negative 1 to the nth power, x to the 2nth power, and the quantity 2n factorial. So there's your cosine function in exact match. Again, same story with the calculator. The calculator really doesn't understand what cosine is. It uses that polynomial to develop the cosine function. And can't stress this enough, tell yourself cosine is an even function, and that'll help you remember and memorize this one. Our third one is a very easy function. In fact, I think I saved the easiest two for last. We got the two harder ones out of the way. They want us to do a MacLaurin series for e to the x. The beautiful thing about e to the x is every derivative of e to the x is still going to be e to the x. So the first derivative is going to be e to the x, and then all the way down, we could go all the way to the fifth derivative if we wanted to, or the nth derivative, and still say it's still going to be e to the x. Therefore, when we evaluate these radicals at 0, we're going to get 1. First derivative evaluated at 0 is 1. All the way down through, we could say that the fifth derivative evaluated at 0 is equal to 1 again. And so we're trying to visualize that generic formula for the MacLaurin series, and then we're just going to substitute all these values into that. And we're going to end up saying that the Taylor series looks like 1 plus 1x plus, let's see, 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the fourth. And I think that's probably enough. You probably get the picture. A couple of things that make this one different than the last two we did. First of all, it's not skipping any terms. It actually hits every single degree term along the way. We didn't skip any over. The second thing is it's not an alternating series. It's just a straight up, well-behaved, every term's positive type of series. Now we're ready to try to develop that nth term. Certainly the biggest challenge on all of these, I believe. Let's see, that's what I get when I plug 0 in, that's what I get when I plug 1 in, plug a 2 in, plug a 3 in, plug a 4 in. So I think this one reveals itself quite handily. We just have positive x to the nth power divided by n factorial, and that's all it is for the e to the x function. If we try to generalize that in sigma notation, we've got our series starting at 0, going all the way to infinity. We've got x to the nth power divided by n factorial, and that is equal, okay, not just approximately, but actually equal to e to the x. And I don't really have any shortcuts for memorizing it. I think this is one, though, if you do have a brain fart and draw a blank on an exam, I think it's very easy to build this one from scratch, okay? I don't think anybody's incapable of running through these steps right here and then building that Taylor series from scratch. But I think we'll use it enough that it'll just come to you and we'll have it memorized quite handily. The last of the big four that they're going to expect you to really have memorized here, and this one takes a little different path than the other three, is going to be the function, and this seems kind of strange, but it's 1 over 1 minus x, and you're thinking, wow, he wasn't that popular back in pre-calc like those other three functions were. But I think the reason that the AP loves this one is because it's built so easily, and we're not going to take the Taylor path as far as taking all the derivatives and going through all that jazz. We're just going to say that it represents a geometric power series, and we can instantly say that it's x to the nth power, assuming that n starts at 0 and goes to infinity. And then if you want to expand that one out, you substitute the 0, substitute the 1, substitute the 2, substitute the 3, so forth and so forth, and you just get this type of looking series. And so that's one they're going to expect you to be extremely comfortable with, extremely familiar with. And I don't know if memorizing is the right word or not, but I just think it's very easy to develop and then manipulate, and we've seen that quite a bit already in the last week. So there's your big four. We're going to have those four memorized, and I'm going to show you how helpful that can become. Okay, perhaps the most important and underappreciated rule within this entire chapter, well, basically, here's what it says. It says if f of x is represented by an infinite series, And we'll just make up a very generic one here. We'll say the nth derivative evaluated at c all over n factorial x minus c to the nth power. Okay. If f's represented by that series, of course, within its interval of convergence, then we're allowed to say that f of kx is represented by this one. All we're going to do is we're going to substitute the kx in for x. That's all we're doing, okay? All we're doing is substituting the kx in for x. And substitution is going to be play a huge role in what we'll see in the next 4 examples. And the type of examples you see in the next 4 really tend to dominate the free response section of the exam. All right, here's the set of directions that we're going to use for the next 4 examples, and we're going to pretend that the exam's asking us to find the first 4 non-zero terms. So notice I didn't specify a certain degree. It's not 4th degree. They just want the first 4 terms and the general term for the following functions. And the first one that I want to throw at you is the function cosine of radical x. Now I want you just to imagine for a sense that you were going to take, now let's see, if you needed 4 terms, we're probably going to have to take, 8 derivatives or so, but the derivatives would get insanely nasty because you'd be taking the derivative of the inner function over and over and over again, and these derivatives would not, I repeat, not be fun, easy, or quick. And so, but what we are going to rely on is the fact that we're going to end up substituting a radical x in for every x that we saw in the original one that we just built earlier in the lesson today. So just recall or remind yourself that cosine of x, and I'm going to talk myself through this one, cosine's an even function. So I need the polynomial with all the even degree terms. The first term, don't overlook that first term. It's actually a 1. That's like x to the 0. It's considered even in this case. Minus x squared over 2 factorial plus, whoops, I got ahead of myself. That's a plus. X to the 4th over 4 factorial minus x to the 6th over 6 factorial. And then we went all the way, negative 1 to the nth, x to the 2n, and then the quantity 2n factorial, finish with a dot, dot, dot at the end. Now, so all I'm going to do for my answer, and this is how quick and easy it's going to become, as long as we've got that first one memorized, is we're going to just start substituting. So I've got radical x squared all over 2 factorial. We've got radical x to the 4th power all over 4 factorial. And notice I'm kind of in slow motion mode now, but I'm just trying to really emphasize the substitutions that I'm making. We've got radical n raised to the 2n power all over 2n factorial. And of course, we can clean that up a whisker. We're going to just multiply all the respective exponents that we see, and we're going to say that cosine of radical x is really 1 minus x over 2 factorial plus, let's see, I'm multiplying a 1/2 by a 4, I'm going to get x squared over 4 factorial minus x cubed over 6 factorial plus, let's see, negative 1 to the nth remains. I'm going to get x to the n power, because I've multiplied a 1/2 times a 2n, all over 2n factorial. And this is an exact replica for cosine of radical x, and there's your first example. Our second example is going to be, let's say they wanted me to build the function sine of x squared, okay, where just the x is getting squared, just to emphasize that. So what I'm going to do is I'm going to remind myself of what the original sine curve looks like, just reiterating the fact that it is an odd function. It has all the odd degree terms, and so we've got x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. Notice we've created an alternating series with all of the odd exponents and so forth. And then we're going to jump to that mysterious nth term. This is the long exponent. We're going to double the n value and add 1 to create an odd number. And 2n plus 1 factorial plus dot, dot, dot. So what I'm going to do is I'm going to run through all of these x's. Every time I see an x, right here, 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 and here, I'm going to substitute an x squared into those places. And then once I substitute that x squared, I can then begin multiplying the exponents. So, and I might do this one a little faster than the last one. My first term is going to become simply x squared. Now my next term is going to be x to the 6th over 3 factorial, because I had an exponent of 2 and an exponent of 3 that I had to multiply. And then on the third term, I'm going to end up with x to the 10th over 5 factorial. Again, I multiplied my exponents of 2 and 5 to get 10. And then x to the 14th over 7 factorial plus ... All right. -1 to the nth power. Let's see. Now, if I substitute an x squared and then I raise it to the 2n plus 1 power, I've got to distribute that 2 all the way through, and I'm going to get x to the 4n plus 2 power. Okay, make sure we got 4n plus 2, but again, the denominator, just like all the other denominators, remain unchanged, and that is our answer for sine of x squared. Our third example is got a little extra twist to it. I'm going to present you with a function x times e to the negative x cubed power. Okay, now as far as organizing this, we're going to break this into multiple steps, but I want you to visualize or pretend that we're only focusing on e to the negative x cubed at first. So my first step today is to just simply substitute a negative x cubed in for all my x's. All right, we're going to substitute negative x cubed. Then, once we get that polynomial built, all right, we're then going to distribute the x that was sitting in front of the e. Okay, so we're going to substitute and then distribute. It has to be done in that order, and we need to stay very organized as we work our way through this. First things first, just remind yourself what e to the x looks like. We need the first 4 terms and the general term. So we're going 1 plus x squared over 2 factorial plus x cubed over 3 factorial. So there's my 4th term plus my general term, or my nth term. All right, first things first, we're going to substitute a negative x cubed in for just the x's. So we got 1 minus x cubed. Then we've got plus x to the 6th over 2 factorial minus x to the 9th over 3 factorial. And then what's going to happen here is I'm going to kind of pull this one apart. Because of the negative sign, I'm going to have a -1 to the nth, and then it's going to leave me with x to the 3n. Okay, if I went a little too fast there, just give me a shout tomorrow in class, and I'll try to break that into a couple of smaller steps to get you there. But I always like to pull, anytime you have a negative inside the quantity that's being raised to the nth power, I always like to pull that apart and just get the -1 to the nth power out front. Now the last thing we're going to do is we're now going to multiply that entire polynomial by x. In other words, we're going to distribute now. So the first term becomes x, the second term becomes x to the 4th, and then we've got x to the 7th over 2 factorial, x to the 10th over 3 factorial. These numerators, you can see, are getting really out of control. They're quite obnoxious. Let's see, I've got -1 to the nth power. I'm going to add exponents here and get 3n plus 1 all over n factorial, and finish with a little ... And you've got a great exact replica of this crazy function x e to the negative x cubed. So there it is, ladies and gentlemen. That's the last one I've got for you tonight. Hopefully that made sense. We've got to memorize those big 4, and then we've got to be comfortable substituting and distributing, and I think we're going to be lights out on these free response questions.